how we use normalizing flow to construct components, various components of particle filters to make particle filters more data adaptive. So when we want to use particle filters in some real world scenario, how we can minimize the lead time from constructing components to deploying those filters. And this is a good part of my former PhD student Xiongje Chen's PhD work. And so in the second part of the talk, I will talk about extension of this piece of work to continuous time particle filtering, so which is his ongoing work as a postdoc in the group. Well, standard filtering formulation, so initially just for the discrete time filtering, and the main difference that we use S here, the hidden states, and the observation or measurements are all indexed by those time index T. And our goal is to obtain the marginal and joint posterior of S given all of the path observation. And here, well, with standard particle filtering, you assume that you know those models, and those models are parameterized by theta. And then we also need to estimate those parameters if we don't know them. There are existing approach on this. I think last week in the summer school, there have been good discussion on them. So maximum likelihood based estimation approach or Bayesian estimation approach to also get a distribution of them. So they can be effective and also nice. However, they often assume that you know, let's say, part of the model or the structure of the model. For example, if you want to use EM-based models, you often need to assume that, for example, the distributions are in the natural exponential family, and then you can construct the sufficient statistics easily for you to perform maximization to estimate the problem. And we relax that assumption, because if we want to use this type of filters in real world scenarios, things can get tricky. For example, if you assume that this is a camera image from the Tesla car, using camera to do autonomous driving, you want to know where you are, and also velocity, and also some potential other hidden states. What do you observe as such an image? How can we construct that relationship between this image and the states that we care about? Because we need to have that information, that piece of information for filter. So besides that, okay, what are the dynamic model? So what distribution family should we choose? So not just about self-driving cars. For example, if we want to run filters on those phones, so there are billions of people using phones, so each have their own dynamics, and then also different relationship between, let's say, measurements and also the states. How can we construct that? So that is related to measurement models. And also with filtering, particularly with high dimensional filtering, we really want to construct effective proposal distribution. How can we also do that with those neural networks? So with those questions in mind, so there were some, well, recently there has been a surge of work on differential particle filters. I think the term has been coined in this paper, and also there are really quite many pieces of work coming after that. So essentially, differential particle filters are about using neural networks for those different parts that I just talked about. So dynamic model, measurement model, and the proposal distribution. But also more, it's much more than that, because, for example, in resampling, the standard resampling operation, multinomial resampling or other type of resampling, they are not differentiable. So we also need to make some change, necessary change. And then we're talking about optimization. So what is the effective loss function for optimization? And also, well, with that loss function, you can compute the gradient and perform gradient descent for optimization. So those are all different aspects of this problem that we can explore, which makes it such an interesting question that I came across in 2019, and then really get quite intrigued about those different parts. So a little bit, let's say, introduction about differential particle filter. So you need to ensure that all components are differentiable, because you need to compute that gradient of the loss function that you design or adopt with respect to the parameter you want to optimize. So all components need to be differentiable. And then, well, those different components need to be constructed with some parameters that you can perform gradient descent. Yeah, so still quite abstract and high level. So I give some concrete example now. So for example, for the dynamic model, some of the initial approach basically use some standard neural network. So the input, the dimension is a same as the state dimension. You put the particle. So assume that a particle, ice particle at constant t-1. You use that as the input to your neural networks, and your output. So some other, let's say, well, output with the same dimension, and then you can add it by some additive Gaussian noise and to form your particle as the output of the dynamic model. And the reason to do this is that if you have an additive Gaussian random variable there, then you can use something called reparameterization trick to make the whole process differentiable. Because sampling process alone, so if you want to sample from a Gaussian distribution, by itself is not differentiable because it's sampling. So there's some randomness of your output, so you cannot really compute the gradient. However, so the reparameterization trick means that you sample a distribution-free random variable, for example, standard normal distribution. So just zero mean, so identity as a covariance. So there's no parameter involved. So you sample there and then you can multiply it by some parameter you can optimize so that you can change the covariance. So then through that, then the whole process becomes differentiable. So this is rather standard. We can obtain this dynamic model. Yeah, I'm going through this rather quickly, unlike in the summer school. If you have any questions, so just know. To get this dynamic model, how about the measurement model or conditional likelihood? So one way to do that, so initial approach is, well, we want to get this conditional likelihood. So P of OT, the observation at the t time, given your, let's say, the state. So you put those two things, so those deep learning based brute force magics as an input of some neural network. And then the output of neural network is just a scalar. So that is your conditional likelihood. That is how they construct this. And it works well when you combine it with, well, with some, let's say, assumption and then problem assumption. But then it's easy to see that there's some problem here. Because here you want to get a conditional likelihood. This is probability density. How can you ensure that this scalar is a valid density with arbitrary?
You mean that the output here is a density function? So instead of just the, like, for example, if you model P or condition S, there's some kind of Gaussian, then so that L theta is not the mean of your likelihood model, but
well, yes,
so it's really the output. So you're really modeling the likelihood density as a via neural network, essentially.
Yeah. So basically, here is not directly modeling the density. Well, it's directly output the density, but it's a fake density because it's not normalized. There's no restriction in this initial project. We'll talk about how we can actually model this as a density. And there are different ways to do that. So I'll just talk about our way of using normalizing flow. I don't know if that clarify it?
Yes, it clarifies. Also, like, why don't we also just model the log density instead of modeling the
yeah, that's a very good approach. But even modeling the log density, I don't think that it will have a normalized conditional likelihood here, right? You just ensure that this is positive or non-negative. Yes. But it doesn't show that, okay, if you take an expectation or integral of this OT, well, we cannot really guarantee that this LTI will have an integral or integral one, right? So that is a constraint of this. And then the consequence, actually initially we didn't notice that consequence until we use this in some of our experiment setup, and we want to maximize the data likelihood. And then with this, let's say, I would say pseudo, or actually I would say fake data and conditional likelihood approach. When you want to maximize the data likelihood, the neural networks will try to always output a very large number because there's no normalization constraint. This is not normalized, this likelihood. So it will always output a large value no matter what is the input. Then in that way, you maximize the data likelihood, but that is not a real data likelihood. Yeah. Yeah, then with resampling, the problem with, let's say, standard approach like multinomial resampling is that you use inverse cumulative distribution function. And so it's a discrete, well, you basically have a discrete output. So your input are those weights, normalized importance weights, and your outputs are those indices of the particles. The small weights, small change in your input, your weights will not really cause continuous update of your output. So that is why the whole process is not differentiable. And the different approach, and actually the first one I would say tricks to deal with this. So the first one is that you don't directly resample based on the actual true normalized importance weight. You resample according to an interpolation between your true normalized weights, so that set of weights, and also a uniform distribution. So in that way, because you resample according to a, let's say, proxy importance weights, you need to correct the weights. So the importance weights after resampling, you cannot set them to 1/n, so n being the number of particles, but you need to have this ratio there. So in this way, all of the resam particles have some weights that are functions of the parameters that you want to estimate. So the gradients will not disappear because this is discrete resampling process. So that is how well you can still retain some information after this non-differentiable process. But the whole process still not fully differentiable because it still involves multinomial resampling. So that is an issue. And that is why there are some other approach. So for example, in this approach, entropy regularized optimal transport resampling. So it use entropy regularized optimal transport method, so through the Synchron algorithm, to basically move samples. So by minimizing the distance between the between the particles after resampling and also the weighted particles before resampling. And then the whole process, because of Synchron algorithm, it is basically a vectorized operation. So it is fully differentiable. However, this causes some issue. For example, bias there, but it's a fully differentiable. I'm not going to delve too deep there because you can see the number of slides there. So I'm going to just assume that we have, those are the existing approach, and then talk about what are the other components and also what we do in terms of resolving some issues I discussed in the beginning. And then in terms of optimization, so we need to know the loss function and objectives. If you know the ground truth, and that is a big if. For example, if we want to know what is my true state now with this phone, you really need to have some person to record what is the time now and what is the actual location. If you think about, let's say, a large scale, let's say Google scale experiments, this can take lots of human resources to know the ground truth, those hidden ground truths. But if we assume that those hidden states are known, so we know the ST star, the ground truth state, you can perform optimization based on the mean square error of your filtering mean. So for example, STI, just ST state, estimated state, that can be the mean of the particles you obtain through particle filtering. But also you can assume that your the posterior following, let's say, for example, Gaussian, then you can basically minimize the negative log collective. So the different approach used there. But then to make it more widely applicable, it is perhaps better to have unsupervised or at least semi-supervised approach. So you can use a much larger number of observations that you don't know the corresponding ground truth. Then we can have pseudo likelihood based approach and also evidence lower bound based approach of your data likelihood to perform optimization. Question? No? Okay. So I'm going to talk about limitation of many of the existing approach. So first limitation, so often they are only able to generate Gaussian prior. What do I mean is that, well, if we look at this example, so it's basically additive Gaussian noise there. So you can only generate Gaussian prior, and then you have Gaussian dynamic model, and you use your proposal for bootstrap approach. So directly the proposal is same as your dynamic model. And then the measurement models are either Gaussian, which I didn't talk about that variant, or do not admit valid probability density as we briefly discussed just now. So those are some of the existing approaches. When I first read that 2018 paper, and then we think about, okay, what we can do. So we have an archive submission.
I'm sorry, just
Yeah.
Are you saying that we can't take gradients, like you can't use the reparameterization trick for push forwards of something that's not Gaussian?
Well, you
Like there
Oh,
are.
yeah, well, yeah,
Yeah.
reprocess trick can also be used for something non-Gaussian, but then there's still limitation about the type of distribution that can be involved with that trick. So what we do here, so I'm going to talk about, is that using normalizing flow to make that distribution that you can adapt to be much more flexible. But that does not mean that this is just the only approach. Thanks for clarification. Another question? So what I'm going to talk about today is well, it's an archive summation, but also it's based on, well, it's an extension of the previous conference paper we have prepared. But in this piece of work, so what we do is to summarize all of those three different variants of normalized flow we need to adapt or design for those three different components of differential particle filters. And also shown you have derived some nice theoretical results that I'm going to present. Just quick introduction of normalizing flow. It is a type of neural networks that are invertible. If the input or if the function is invertible, so we can use change of variable to compute the density. And also, well, how about conditional density? Because, well, when you compute the conditional likelihood or the proposal is conditional density, well, there's also variants of normalized flow called conditional normalized flow. You can have a conditioning input U there as an input of that neural networks to perform this change of variable computation. And this is just one variant of conditional or normalized flow. So you have you split your inputs into two parts, and then one part of the input is directed output to the put into the output, but the other part is just a transformation of those two parts. And then by some, well, with some design choices, for example, like this one, I'm not going to go into detail, but then we can actually show that this will lead to invertible transformation. Basically, any different inputs will, by construction, give different outputs and vice versa. And also with this one, it's very easy to compute the gradients. So for us to perform change of variable calculation, because that is what you need to perform the computation. And then with conditional normalizing flow, so there's a conditional coupling layer involved. It's very straightforward. This is just a standard normalizing flow. The only thing you need to do is to put the conditioning part as an input to some of the functions involved in the normalizing flow. So get the conditional normalizing flow. So basically, essentially, here that instead of just have exponential of this C with X as an input, well, the conditioning part is that we can have this O as also an input to that C function. And then again, you get an invertible transformation, but with those observation as an input. And so in essence, what we do, so first to make the dynamic model more flexible, we can directly use the, let's say, more, so the initial Gaussian type of dynamic model. So you pass the particles through the neural network, add some Gaussian noise, get this as tilde Ti, and then you stack it by a normalizing flow, and you get a flexible, let's say, dynamic model. But we actually don't propagate particles this way because this is bootstrap particle filter approach. So we actually have a proposal distribution to do this. So what it does is that this separate neural networks takes a particle as a previous time step and also observation as an input. Get some output the same dimension of your state, and add some Gaussian noise, and then add another layer of the conditional normalizing flow there. So which basically means that you can get a quite flexible proposal distribution, and then we optimize all of the network parameters in a way to maximize the objectives that you care about or minimize the loss function you care about. And then the quick, you can say that for this type of normalizing flow, just now I talked about the introduction of normalizing flow. One thing that we can note is that the input and output have the same dimension, because that is the way you construct those invertible transformation, right? And then so that's why you can see that for the standard normalizing flow, the state as a previous time step to go to the state as a next time step, they have the same dimension. They are in the same space. For conditional normalizing flow, so take away the conditioning part, those are on the same, let's say, dimension. And that really gave us a, let's say, raise a question, how we can use normalizing flow. Well, by no means this is the only approach, but can we use also normalizing flow to construct the likelihood, conditional likelihood? Because just now, as we saw in the previous example, the output of that conditional likelihood is a scalar. But here we require them to be have the same dimension. So what we can do is essentially, so this is a previous approach. And what we can do is to actually have a conditional normalizing flow, generate a Gaussian sample, the same size of the state observation, so in a space Y. And the reason we can do this is that conditional normalizing flow is invertible transformation. So we basically can compute, let's say, the density of the probability of OT, or in this case, so density of OT given ST, based on the density of this Gaussian sample. Because when you pass any OT or STI through a neural network, get some output, and then you assume some prior distribution of this Gaussian, for example, just a standard normal, you can compute that density. And you can compute the original density P of OT given ST through change of variable, right? So that is how you can get, let's say, normalized conditional likelihood. So essentially, we get valid probability density here. So P of OT given ST. So we evaluate this P of ZT. So ZT basically has the same dimension of the observation. And then you evaluate also the change of the density through the change of random variable. And then we can, and the benefit of doing that, once we have a valid probability density constructed here, we can use this really increase the type of optimization objective we can use, because now we can use likelihood-based loss function to compute as our target objective function. Because, for example, for this, let's say, likelihood-based function, it needs to be able to compute this P of OT given ST, and now this can be directly computed as we show there. In terms of theoretical results, so basically, for standard particle filtering, where we know that the mean square error of quite some notation here. So basically, I first say so alpha t is just a predictive distribution, and alpha nt is essentially the approximation of the predicted distribution. So the first one basically shows that, well, if we want to compute the expectation of some test function psi, and then using the particle approximation to compute that empirical expectation, so that mean square error is as order of 1/n. And we can do the same for this beta t, which is a posterior time step t, and then beta nt just a particle approximation there. So this is just for a standard particle filter, and this is a mean square error. And then we want to establish what is the mean square error, so consistency property for the normalizing flow-based particle filter. We kind of inherited many of the assumptions in this paper that proposes optimal transport-based resampling approach. So essentially, there are four main assumptions. So the first one is that the state is on a compact space. The second one basically shows that optimal transport is kind of regular between the predicted distribution and the posterior. And the third one just shows that the translation kernel is not something crazy, so it's smooth. And the last one just basically shows that the likelihood, the conditional likelihood function will also not give you some strange behavior. So there are some vastness and distance is bounded, something like that. And then the results we obtained is that the mean square error of the let's say particle approximation of the mean of any test function here is in the order of 1 over n to the power of 1 over 2 dx. So Xiongje has done some really nice work here. So it's not as good as 1 over n. The main reason is that the optimal transport-based resampling approach is introduced. So there's some bias introduced there. And so there's really limited theoretical work in this part. So if you are interested in this, so I think there will be some really nice direction that we can explore. Okay, without
Sorry, just the one we had in the paper was 1/8, right?
yeah,
1/8, 1/12.
yes.
What's the argument that made you get the 1/2 instead?
Yeah, so I discussed with Xiongje how we can explain that. He actually made some nice derivation area, and then we found that it's not, there will not be enough time to go through all of the details. So it's not exactly the same assumption. And also, I think there are basically different derivation involved there. So it inherits the original derivation and assumption, but most of the assumptions there, but there are different approach involved. Xiongje can discuss more details there. So the duration, yeah, I'm not sure how to, yeah, I think we'll have some. Not going to go through all of them. There's some nitty-gritty detail there to sort that out. So basically to improve from 1 over 8 dx to 1 over 2 dx. Yeah.
We inherited the 1/8 from essentially contractions of transport plans, if I remember correctly. I have not looked at it for a while. But then, like, have there been like recent results on that, or?
Yeah, so these are the recent results. So the full details also can be found in the archive paper we put there, and also it's big part of, well, good part of Xiongje's thesis. Yes, this is more like new results. Happy to discuss more. Xiongje is online. Discuss this part.
I'll just look.
Yeah, I think well, I think it's probably better to discuss offline. I think that there are some something that he found that can be improved in the original derivation. So that is how the different. Yeah, it's always like that, right? Okay, so now let's talk about the numerical results, assuming that there are no other question. And so one of the initial numerical experiments we have done is this simple disk tracking, or this interesting disk tracking example. So very simple. The state is the location of the red disk shown on the upper left here in this image. So just 2-dimensional. And then the observation are the images. Images of those different disks of different colors. So those with different colors are distractors. And then, well, the question is that if one want to use Kalman filter or particle filters for this, what is the likelihood? So what is the density of this image given that 2-dimensional state? So it's very hard for us to construct by hand. However, using this approach, then you can really save your efforts to construct those components. And well, those are just a setup of the state, well, the dynamic model, and then those are the loss function we use. So basically here we are performing supervised learning, assuming, because simulation we know the ground truth. So basically you want to minimize the mean square error. And also because we also use some encoder, the images are really in a much higher space. So that is why we have an encoder to map the observation to some encoding ET, but also you don't want those ET to be uninformative. So you want to also reconstruct the observation based on ET, and that is involving this autoencoder type loss there. So we also want to minimize this. We evaluate this with respect to a few methods, and then what we use to train that 500 trajectory, each with 500 time step, 50 time steps, and then 50 and 50 for validation and testing, and 100 particles in both training and testing. There are some, let's say, animation there. Perhaps I should restart. So initially you have your state here, the ground truth here, and then, but we don't know about that. You spread the particles uniformly across the region. So that's why it's everywhere, and this is your particle mean, and they are distracted there. So it's quite far away from the true state. But then you can quickly, so there's an offline training stage, so learn about those dynamic model and element model, and then you perform, let's say, the normal particle filtering procedure, and you can see that quite quickly the particle means start to converge to the true target mean. And then if we compare the performance, so the Normalising flow differential particle filter has the smallest root mean square error compared to the other opinion. And then in testing, it also has the smallest error. So very quickly, as you continue the field. There's a different, let's say, there's another experiments we have explored, and there are a few more in the paper. So this robot localization one, it's again numerical simulation. So it uses Google DeepMind's, say, the maze simulator. So the state is a XY position plus orientation of the robot, and then the observation are those robot cameras, and just the robots move up along the maze, and then what we want to do is according to those sequence of images, to infer where are those robots based on the images that you see at each time step. And then, well, those are the dynamic model, and then the training criterion, so 900 trajectories, 100 for validation and testing, 100 particles for in training and testing. In some simulation here, basically you start from a number of particles without knowing where the ground truth location. And then after a while, particles start to converge towards a true location, and then that is what makes us happy. Right? In terms of the training performance, you can see that this converges fastest, and also to the lowest value, and also in terms of testing with different maze environments. So those are separate experiments we have done with different, let's say, maze size, and then it always leads to the smallest test errors. So in summary, so in this piece of work, we introduce a normalizing flow-based approach to construct flexible and valid dynamic model, measurement model, and also proposal density. So it can be solved as a plug-in method. So for those existing approach, you can see that from the diagram that I have shown here, those can really just be, let's say, plug-in stack onto existing differential particle filtering components, as long as those, let's say, base distributions, they are valid distributions, so you can perform change of variable transformation. And then so they are differentiable and also consistent, as we showed there. Okay, quickly, I think I have a little bit time to talk about the continuous speed work because it's such interesting. So, for example, now if we are happy with the performance on Earth of this filter, and we want to extend this to Mars or to Moon, so you send a rover there, and then you really face, let's say, unknown environment and also unknown dynamics because of the environment, how we can perform, let's say, filtering. But then if we think about this problem, is that you don't even have, let's say, regular time samples or observations, because, well, with those, let's say, transmission of signal, you really have, let's say, missing observation in irregularly distributed time grids. How can we perform filtering? And over the past week, I was talking to various friends. So I'm working more and more in dentistry here. So what is the connection with sequential inference? So here's a dental images of the same person taken at 2 different times. You can actually see there's some disease progressing. So for example, the bone loss levels I can see from the dental images grown from here and here. But also the 2 pictures are really taken by different machines. You have 2 different data distribution. The point I want to make here is that not just data distributions are unknown and also changing, but also the disease really progress continuously. You don't have the regular time step, and also you don't have regular dental visits. So you really have this continuous update of your states and also irregular observations. So how can we perform filtering? Well, it's basically almost the same type of state space model. The only thing that we change from the discrete dynamic model to dynamic model, the continuous dynamic model, model through a stochastic differential equation. And then, well, here, those drift term and also diffusion terms have parameters, let's say theta. If we know those theta, we can filtering. But how about if we don't know about filtering those parameter values? So how can we learn those parameters while we perform filtering? That is essentially what we want to do in this ongoing piece of work. And because this ongoing piece of work, we don't have an archive paper, and then it's really a good place. So if you are interested, you can provide suggestion and we can start with it. I think also another good part of continuous discrete filtering is that we can actually infer the posterior at arbitrary time instances if we can learn those thetas. Linear Gaussian is common Bussi filter with nonlinear non-Gaussian model. We can have continuous discrete particle filters. So what are the components of those continuous discrete particle filters? Well, basically there are 2 processes, stochastic processes. So there's a dynamic process, as we show in our dynamic model, but also there's a proposal process. So how we can also use observation to move those particles into more effective space. So if we accept, well, if we have those 2 processes, and also we have a way to construct the measurement model, how can we update the particle weight? And the rest of the thing in this continuous discrete particle filtering is the same as a standard particle filtering in discrete case. Perform particle weight update, you perform resampling. The existing approach on this, well, what we want to do here, so the goal is to have a data adaptive continuous discrete particle filtering. So we build the state dynamics and proposal using neural SDE, and also we build measurement model with neural network. Essentially, we build that measurement model using the conditional normalized flow that I just mentioned. The more difficult part is really this part. So neural SDE was an extension to neural ODE. Basically, it is using neural networks to construct the drift term and also diffusion term in a stochastic differential equation to model the dynamics. And then the name neural ODE, neural SDE really, well, the essential part is how we can perform effective grading computation. And both approach use the ordinate sensitivity method to make the whole process efficient. And it's a natural choice when dealing with stochastic dynamic model. I think I want to quickly jump to show what is the challenge. The challenge is that if we use neural SDE to move those samples, your transition density are intractable, and also your proposal density are intractable. And the second one is easier because we can directly use conditional normalized flow. And then what we could do is, instead of evaluating the density directly, generated of those samples generated through those neural SDE, we can find an unbiased estimator of this ratio. Because if we have that, we can use random weight-based particle filters to perform particle filtering and then get a valid particle filtering algorithm. So if we don't do that, well, one option is that we can use bootstrap particle filter. So we don't need to evaluate those density. So we just use the likelihood to update the importance weights, but then in high dimensional spaces, this can give us weight degeneracy. So we use this random weight approach, and then it's basically everything is similar to the standard particle filter, except that we can compute, let's say this Q. This Q is a random variable with expectation of this Q the same as an incremental importance weight. And how can we do that? Well, we basically can use a Gaussian theorem to compute this. So it's a little bit complicated, but this is something doable and still very early exploration. So I think I probably will just want to quickly show some of the initial results we have done. So in some simple experiments. So first experiment is this Benny-Stone filtering problem. So the state evolves according to some ordinary stochastic differential equation. Then we perform filtering and learn those dynamic model and measurement model has some good state estimation performance. And also we have used this in some noise pendulum system experiments, also getting some encouraging initial results. But the problem here is that there are a number of unbiased estimator of the weights that I just talked about. We use a Gaussian theorem. This seems to be a straightforward choice. But how about the other type of estimator? Which one is better? And also in terms of the theorem that I really didn't get a chance to talk about, that Xiong derived to show that this will indeed give us an unbiased estimator. So this Z is based on the assumption that we can perform exact simulation of those neural SDEs. But however, in reality, you need to have discretization. So it will not be exact, so those theoretical results actually won't apply. How can we do that? And also there are system identification problem because there will be different latent dynamics and also measurements that can lead to the same observation, but then this can produce poor filtering results. So how can we address that? So those are some of the interesting and also unknown. So I think I will stop here. Sorry for going over time.
Any questions?
I have one question. So